Hello AP Chem students and welcome to topic 8.5 acid-base titrations. The learning objective for today is 8.5.a, explain results from the titration of a mono or polyprotic acid or base solution in relation to the properties of the solution and its components. So let's look at it. As always, my computer is going to be very slow to respond. There we go. Okay. So starting off with the equivalence point. So remember, we already talked about this in topic 4.6. We examined titrations and looked at the titration of a strong acid and a strong base. When we graph this data with a strong base, I should say, when we graph this data, we plot pH on the y-axis and the volume of titrant that's been added on the x-axis. And so you can see that on the graph here, right? Here's pH and then here's the volume added. So remember that in every titration at the equivalence point, right there, your moles of acid is equal to your moles of base. Because of this, calculations at the equivalence point are simplified by using the equation MAVA is equal to MBVB. That's a little typo. That is supposed to be a B there. So I want to point out one thing. You're used to seeing the equivalence point at 7. We're about to look at some situations where the equivalence point is not at 7. And so the way you actually find the equivalence point is it's the point at which the graph changes curvature. So if you're in calculus, this is something you've talked about, but you can see here how the graph kind of curves down. And then at this point, the graph switches and it curves up. So it's right there in the middle of that S. That's your equivalence point. Okay. So we're going to talk more first about this strong versus strong titration. So titrations of strong acids with strong bases go all the way to completion. Because these titrations attain neutralization, result in neutralization, stoichiometry, also known as a BCA table, which you know and love, is all that's required to solve this problem. Now, one note, I'm going to talk on this slide about having an acid in your flask and then titrating with a strong base, but you can invert it and it would be just exactly the same process, except the species, of course, this graph would be flipped, and then instead of starting with acid and ending with base, you would start with base and end with acid. So I'm just walking through one version. So before the equivalence point before the equivalence point, on this graph, the species present are going to be the strong acid and the spectator ions, right? So for example, a common strong acid, strong base reaction, titration, is with sodium chloride and, is with hydrochloric acid and sodium hydroxide, forming sodium chloride. So the sodium and the chloride are present in solution, but they're not actually participating in the reaction. So they're there, but they're not actually undergoing any chemistry. So the strong acid is what's dominating your calculations here. And so you'll do a BCA table to figure out how much of your original acid remains, and then in terms of moles, and then you would divide that by the total volume, and that would give you your concentration of H+. And then if you wanted to, you could do the negative log of that to get pH. But usually that's not a situation we do with the graph because you can determine the pH by looking at the graph. At the equivalent, although you could work backwards as well. At the equivalence point, your species here is a neutral salt, and that's going to be the neutral salt of the spectator ions. So that sodium chloride we were talking about. Because remember neutralization, that we're forming water, and acid-base reactions happen in water. And so while we're forming water as part of the reaction, we don't talk about it because there's so much water in solution that adding more water to it is just a minimal change. So neutralization is the process of forming water, and that's really important for you to understand. But in terms of the calculations, the water itself that we're forming in the acid-base reaction is not actually something that we need to take into account. So we do need to take into account the neutralization part, right? So the acid and the base reacting with each other. Okay, so at the equivalence point, you've got your MAVA is equal to MBVB. There is that same typo again. Sorry about that. At your equivalence point. Past the equivalence point, you've got your neutral salt and the strong base, because your strong base is in excess past the equivalence point. So then you would again do your BCA table to determine the moles of excess base, and then you would divide it by the total volume. And that would give you your molarity of OH minus. Okay, so now let's talk about a weak acid, strong base. So you can see we've got this strong curve still showing on the graph. So you can see that there's a very different shape to the curve when we're doing a weak acid with a strong base. So with a strong acid, you see that this curve is down like this, right? Whereas with the weak acid, it goes up a little. And also the strong acid doesn't have this kind of, what I call tail at the beginning, right? Right there. But the biggest thing is that this remains more or less flat. And you can see it's flat, 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 and then a sharp rise. Versus with the weak acid, we have this gradual slope, and then we have that sharp rise. But even the sharp rise is kind of condensed, right? So it's not as tall, as much of a jump when you go from the strong acid here up to where you'll be past the equivalence point. So we're going to talk about why that is. So first of all, your species present before the equivalence point, so in this range over here, would be a weak acid and some conjugate base. So because you have both of those present, that means you have a buffering region. Okay, so this portion of your graph is acting like a buffer. And that's why it has the shape that it does. You don't see a sharp increase in pH in the same way that you do when you have a strong acid, strong base titration, because you have this buffering region. So before the equivalence point, you're going to do a BCA table, again, to figure out how many moles of weak acid versus how many moles of conjugate base have been formed. And then you can either do a weak acid ice calculation, or you can use the Henderson-Hasselbalch equation. And we'll talk about that not until topic 8.9, but it's worth mentioning here because once you know about the Henderson-Hasselbalch, you can come back and use it in this situation as well. At the half equivalence point, we have a very special situation. So there's your half equivalence point. So it's literally half the volume that it takes to get to the equivalence point. So you can see here our equivalence point is at 25 milliliters. So your half equivalence point is at 12 and a half. So at your half equivalence point, half of your weak acid has reacted with the strong base. And so half of your weak acid has turned into conjugate base. That's important. When you have equal molar conjugate base and weak acid, that's what we would consider an ideal buffer. And then at that point, your pH is equal to your pKa. Now, we know this fact to be true because of the Henderson-Hasselbalch equation, which again, we're not going to get to until topic 8.9. So for right now, this is just kind of a point of memorization, but it is an important point and we use it frequently. If you can remember that at your half equivalence point, your pH is equal to your pKa, you're going to be able to simplify a lot of questions and also answer some questions directly without having to do calculations, which is a massive time saver. At your equivalence point, you've got your basic salt present. So remember that with strong acid, strong base, we had a neutral salt because we had the conjugates of strong, and the conjugates of strong acid and strong base are very, very, very weak to the point of being neutral. Here, because we have a weak acid, the conjugate base of a weak acid is relatively strong. And so it's strong enough that it actually changes the pH of the equivalence point to being basic. Really common misconception. Students think that it's basic because of the presence of additional OH, but it's not, because remember here at your equivalence point, your moles of acid is equal to your moles of base. So we do not have excess sodium hydroxide. We only have the salt that's present, only the conjugates. And so that must mean there is a conjugate species that's changing the pH of the equivalence point, and it is the conjugate base. Okay, so your calculations here would again be MAVA is equal to MBVB, same typo. But again, noting that your equivalence point pH is also impacted by the presence of the basic salt. Okay, so then your basic salt plus your strong base are going to be your species present past the equivalence point. But past the equivalence point, the strong base is going to overwhelm any contribution from the basic salt. And so your calculations then come back to being simple stoichiometry calculations with the BCA table. And then the moles of base in excess divided by your total volume will give you your concentration of OH minus. So you do get to ignore the basic salt when you go past the equivalence point, again, because that strong base is going to overwhelm the system, and any basicity that's contributed by the basic salt at that point will be minimal, probably even ignorable once you take significant figures into account. So now we're going to talk about polyprotic acids. So all of my clicks are out of order. So a special class of acids exists called polyprotic acids. They include diprotic acids, where you such as H2SO4, triprotic acids, such as H3PO4. These are acids that contain multiple hydrogens, and the acids show multiple equivalence points because they dissociate stepwise. So you can see diprotic has 2 hydrogens and triprotic has 3. So these calculations would need to be approached stepwise. most of the time the first dissociation dominates the system and thus the calculations. As you go through the dissociation of a polyprotic acid, you can see that your Ka values become smaller. So your first dissociation tends to overwhelm any remaining dissociations. In this class for AP, the main thing they want you to be able to do with polyprotic acids beyond the first dissociation. So you can certainly do calculations with the first dissociation. We could go beyond that as well. But in this class, you really they don't ask you to beyond the first. What you do need to be able to do is identify the species present in each portion and identify the pKa for each dissociation of each proton. And so you would do that by looking again at your half equivalence points. And so that's shown nicely on this graph here. So here's your first equivalence point, that first inflection point. That's what inflection point is what it's called when it changes curvature. And so here's midpoint 1. So that would allow you to see pKa1. If you look at this, like here's 2 and here's 4. So, you know, it's kind of hanging out in the 2 range, and that makes sense because Ka1 here is 10 to the -3. And then here we can see midpoint 2. So that looks like it's around pH of 5. So actually we might be looking at 2 different acids here. And then at your third half equivalence point, you can see that our pKa we would expect to be somewhere around 9 because this is around a pH of 9. Okay, so that's polyprotic acids. So let's check out weak bases versus strong acids. So here, before your equivalence point, you have a weak acid and some conjugate, a weak base and some conjugate acid. Again, that's going to set up I didn't label it here. That's going to set up a buffering region again. So you're going to do a BCA table. Then you can either do your weak base tables, or you can use the Henderson-Hasselbalch since you have the buffering region. I thought I had that labeled. At your half equivalence point, you have equal moles of weak base and conjugate acid. So your pH is going to equal your pKa again, but it's important to note that the pKa is the pKa of the conjugate acid, right? Because we're starting with weak base. So then if you needed the pKb of your weak base, you can use the relationship of pKa plus pKb is equal to 14 for conjugate acid base pair. At your equivalence point, you're going to have an acidic salt. So that's going to be the conjugate acid of the weak base, which is going to drive the pH of your equivalence point below 7. But again, you can do that MAVA is equal to MBVB with my same typo that I keep copying over. And then past the equivalence point, you have your acidic salt and the strong acid, just as we saw with our weak acid strong base titration. At this point, your strong acid is going to dominate the system. Therefore, you can use a BCA table to figure out your moles of acid. That should say acid. Goodness, I've got a lot. Oh, there's my label for buffering region. Apparently, I didn't proofread this as well as I should have. So your moles of acid in excess divided by total volume here past the equivalence point. Okay, so sorry about all the typos, but what should you be able to do with this? Well, number 1, produce a titration curve. So you should be able to sketch it. Specifically, knowing the curvature and the difference in the appearance between the titration of a strong system versus a weak strong system. Okay, so that'll be important for you to know, particularly noting the buffering region right up there. You should be able to identify key areas on the titration curve, including the equivalence point, the half equivalence point, and the buffering region, if there is one. Use the shape of the titration curve to determine the protonation of the acid. So in other words, is it a monoprotic acid, a diprotic acid, or a triprotic acid? And then finally, identify the major species present at any point on a titration curve. We've often seen that assessed with particle diagrams. And that is it. So I will see you soon for topic 8.6, which is molecular structure of acids and bases.